Hello, my name is Mashari Alimadi. I'm a third-year student in electronic engineering at University of Surrey, and today I'm going to present my dissertation project, which is the design of a Braille system using P20 cells for visually impaired people. Before we go deep in details, I would like you to have a quick look at the content overview. We will start with an introduction, then we will move to the literature review. After that, we will look at the aims and objectives that I have set at the beginning of this project. We will talk about the components that is involved in our system. Then we will have a quick brief about the hardware design and the software design. And finally, we will end this presentation with a brief conclusion. In our world, there are numerous kinds of people based on country, religion, caste, language, color, disability, and etc. However, in this presentation, we are going to focus a little bit on the term of disability, and especially those blind people. A considerable category of people are blind, but at the same time, some of them are deaf as well, which seems very heart-wrenching for a normal person, as how those people can communicate with others, or even entertain themselves with reading, for example, which is the simplest task that a normal person can do. Have you ever thought of how hard for them to practice their daily life activities, especially in this digital era, where almost everything is being carried out in digital manner? Braille can be defined as the physical writing approach for vision-impaired people with letters on an uneven paper. Every word and digit in the Braille language has its own combination. In other words, a special format of dots, as shown in the figure. With the help of the development of technology nowadays, we have managed to create a Braille system with 8 cells that uses each dot of cells systematically according to different alphabets. In our system, a message will be received wirelessly from a smartphone, and then every character in that message will be transformed into a unique text in the form of 8-bit binary digit. Finally, the text message will be displayed in Braille language on the translator device. We want the communication between a normal guy and a blind person to be very possible and easy at the same time. We are giving those people an opportunity to interact with the age of technology, not only to communicate with others. This section shows some of the electronic devices that were designed previously by several innovators in order to help blind people. The figure on the left side shows the Braille system of next generation. The very smart thing about this project is that they have used GSM modem that receives SMS messages from phones wirelessly, so meaning without using a wire or a cable. Then it will send the data serially to the microcontroller. However, the 6 dots of the Braille letter sequence are indicated by vibrated sensors, which can only represent a single character at a time. Those sensors will oscillate in a particular pattern to represent the letter that has been received. Another disadvantage of this design is that client must press a key after every word in order to change the series of the status received. And this is a very long time process, believe me, and totally not comfortable for the user. The next figure shows the Braille system implementation that uses Raspberry Pi as its microcontroller. In this design, a Braille letter is displayed using solenoids, which is encapsulated by a box having 6 slots for each solenoid. I believe a few changes are needed for more improvement. As it can be seen from the figure, the circuitry is extremely large, which is not suitable to be sensed by a fingertip, for example. Similarly, it can only represent a single character at a time. Also, you need a cable to send the data from the phone to the microcontroller, which is another disadvantage of this design. Finally, you can notice that both of the examples given were having only a single way of communication. We have studied all of the examples, trying to learn from their mistakes and then improve our design as much as possible, seeking more convenience for the user, of course. Our goal is to have a system that receives a message from a smartphone using a wireless communication channel. The message will be converted into binary digit numbers, and then 8 Braille cells will display that message in Braille language. How? By raising all of the dots of each cell, taking into account the special format of each character in that received message. After that, the user will be able to read the text by sensing the raised dots on each of the cells and then understand it. In order to have a two-way communication system, we have added a keypad with 11 push buttons that will be used by the client to type any particular text in Braille language. The text will be again converted from binary digit numbers to normal sentences, and then it will be sent all the way back to the smartphone. The whole system must be designed in such a way that it will consume less power, portable to carry, easy to use, and most importantly, with low cost. In this part of the presentation, we are going to talk a little bit on the hardware components that we have used within the Braille translator device. As for the brain of our system, it was decided to use the Arduino Uno, which has a built-in microcontroller chip of Atmega 328P, combined with other passive and active components. The Arduino Uno can be supplied with a voltage ranging from 5 volts up to 12 volts with a clock speed of 16 MHz. This means that the Arduino board is capable of performing 16 million tasks in only a single second. It also has the exact amount of digital and analog pins, which we will need for the keypad, for the push buttons in other words, and many other components that we will discuss later. We could have used the Arduino Mega, which has higher processing speed and more pins than the Arduino Uno, but on the other hand, it will increase the cost of the device, and it will also take up more space in the enclosure. Finally, and the main reason behind our choice of this board is that the Arduino Uno can be easily programmed using either C or C++ languages, unlike Raspberry Pi, for example, which I find very tedious to do. Next is the P20 Braille cells that we are using in our system in order to display the translated text in Braille language. On the top of each cell there are 8 dots, which are driven by piezoelectric actuators of bending type. The cell must be powered up with supply voltage of 200 volts with only 5% tolerance, meaning that anything below 185 volts won't actuate the cell, and anything above 215 volts will damage it immediately. According to its datasheet, the dot rising time of the P20 Braille cell when information is received is about 50 milliseconds, which can be considered extremely fast and very efficient as a component to be in our system. Using one Braille cell is not enough for a proper use, as it will only display a single character at one time. Therefore, it was decided to use 8 P20 Braille cells. The higher the number of these cells, the higher the efficiency of the device. In order to drive all of the 8 Braille cells in multiple mode by serial communication, we have to use an active back panel, as shown in the figure. A single back panel is capable of connecting 8 Braille cells together. So what if there was a system requires 16 Braille cells, for instance? You will just have to use 2 back panels connected together, and therefore you will be able to connect all of the cells with it. The second figure shows the pinout connection of the back panel. It can be seen that it has 2 types of power supply. The first one is the 200 volts, which is used to power up the dots on each of the cells connected to it. The second terminal is the 5 volts. It uses low voltage to power up the cells connected to the back panel board. We have mentioned previously that we are going to need a power supply of 200 volts in order to operate the P20 Braille cells properly, except that we don't have that amount of power supply in our power conventional grid. Therefore, it was very necessary to have a DC to DC converter that can convert 5 volts up to 200 volts DC. The converter has 4 pins as shown in the figure: 200 volts, ground, 5 volt, and on. The on is an input control pin that turns the supply on when it is low and off when it is high. It should be noted that the on terminal must not be unconnected while using the converter. That's a big hazard. According to the datasheet, the converter can be used with maximum 40 Braille cells without any problems. However, connecting more than that will cause the dots on the Braille cells to move very slow. And instead of using a cable to send the information from the smartphone to the Braille system, we have decided to have a wireless communication channel. This can be easily implemented using HC05 Bluetooth module. The supply voltage of the module is 5 volt, which is feasible for our project. It also has a range of 100 meters approximately. More than that, it can be easily used with many Android applications available for smartphones. Therefore, we can make the process much easier. However, the main reason behind our choice of this module specifically is that it communicates using the USART, which is available in most of the microcontroller modules, such as the Arduino Uno we are using. I mean that we don't have to install any kind of libraries when programming it. Finally, we are going to talk about the last component that have been involved in our Braille system, which is the LCD. The LCD we have selected has a 16:2 display screen, meaning that a total of 32 characters can be displayed on that screen at a single time. So, I know, apparently you're asking yourself why there is an LCD included in that translator device, even though that the user is totally blind. The reason is that we wanted to verify what is being sent from the smartphone to the microcontroller. I wanted to know whether the Arduino is receiving the exact message that I have sent from my smartphone or not, even before translating this message to Braille language and displaying it on the translated device. So, I can assure you that the LCD is an unnecessary component and it can be removed from the whole system. However, we have just included it for verification purposes. Moving on to the next part, which is the hardware design of our Braille system. This part has been divided into several stages. First, we had to design the circuit diagram on Eagle software. As can be seen from the figure represented in the slide, this is the whole schematic diagram of our system. We can see that the LCD display has only 4 pins, and this is simply because we have used I2C module with it in order to reduce the pin connections between the Arduino Uno and the LCD screen. We also can see that the 5 volt enters the DC to DC converter and it output for us a rail of 200 volt, which enters the back panel of the Braille cells, so we can power up the P20 cells. The Bluetooth chip has also 4 pins, ground and 5 volt, RX and TX. The RX is the receiver, which is connected to the transmitter of the Arduino and vice versa for the transmitter. Basically, it's connected to the receiver of the Arduino. There's a bunch of push buttons, as you can see, a total of 11. Send, clear, enter, and other 8 buttons, which is the total number of the bits we have. We can also see a potentiometer on the left of the Arduino. We're using this potentiometer as an accelerator to speed up the time of displaying the characters on the Braille cells. The second stage of the hardware design was basically designing a PCB for our Braille system prototype. Similarly, we have used Eagle software again. You can see that there is an Arduino shield on the bottom layer of the PCB that I have designed. And this is simply because I wanted to connect the Arduino with the PCB using male headers instead of using wires to reduce the empty space inside the enclosure that I will design later. After the PCB has been arrived, I have tested it and connected it to the components of the Braille system. Everything was working as expected. This is a very important stage as we want our project to be more professional. This is the third and the last phase of the hardware design. In this part, we have designed a 3D enclosure for our final prototype of the Braille translated device using a 3D CAD modeling software known as Fusion 360. All of the necessary dimensions were taken into consideration while designing the enclosure on the relevant software. It was very important to have the perfect fit that ensures functionality, cost effectiveness, and safety. The enclosure were designed in such a way that it will lock the top layer with the bottom one without using any kind of screws. As you can see from the figure on the right, this is a picture taken from the enclosure while it's under section analysis. So basically you are seeing the enclosure cut it in half. You can see that when you push the top layer with the bottom one, it will lock using a method called clicking. This is a very smart method for small electronic project, so you can have an easy access while presenting to the audience and to show what's inside the enclosure. The figure on the left side shows the final look of the 3D enclosure that had been designed. You can see that there were some labeling beneath the button holes for the push buttons, and this is simply because I wanted to test the device, and when I type in Braille language I wanted to verify what I'm typing. Am I hitting the bit number 3, or does the Arduino just give me random values? This part of the presentation explains some of the software principles that have been followed while writing the code of the Braille system. As it was mentioned earlier, each of the P20 Braille cells has 8 dots, in other words 8 bits, and every bit has a specific value. In order to find this value, we need to use the formula of 2 to the power n, where n is the number of the bit. For example, bit number 4 has a value of 2 to the power 4, which is 16. Because we are using a total of 8 Braille cells, we have to declare an array that can store 8 numbers at a time. Now, in order to raise a specific dot of a specific cell, we need to save a variable of any value from 0 up to 256. But this will only raise random dots on random cells. Here comes the most important part. In order to convert the normal text into Braille language, we must have a Braille mapping for all of the alphabets and numbers. Let's take the lowercase of the letter A an example. We know that this letter is represented in a Braille language by raising the first dot only, which is bit number 0. Therefore, in a Braille mapping, we must declare that the letter A with the lowercase is equal to 1. And the same procedure must be followed on the rest of the characters and the alphabets. The bottom picture shows some of the Braille mapping that have been implemented in the software code. Nowadays, there are many people who suffer from blindness, and unfortunately the number is increasing. They face difficulties in every day trying to seek help from other people who can sight, just to read them a certain passage, for example, such as price and size. As the Braille translator device allowed them to communicate with others, it also allowed them to learn new things such as vocab and grammar. This device can also be used to teach children in schools, blind children. I fully believe that those people should not just left behind when it comes to technology. I believe that they are capable of interacting with this digital era. Finally, we can state that our project went very well and as expected. Every goal and aim that we have set at the beginning of this project has been accomplished successfully. Thank you.